Hello, this is a video of our MPMC project. The title of our project is Time and Motion Based Streetlight Intensity Controller. The members are I, Anirudh Ramesh, Keerthanan, and MS Praveen, under the guidance of Dr. Abraham Sudarshan Pondraj. The basic idea of our project is to control the LED light intensity via pulse width modulation using the 8051 microcontroller. So, we are using a time-based schedule to manage the intensity of the light. From evening 6 p.m. to 12 p.m. when the traffic is heavy and more pedestrian movement is detected, the light stays at 100% brightness. During the late night hours, let us say 12 p.m. to 6 a.m., when there is no vehicle movement or reduced vehicle movement and pedestrian movement, the lights are dimmed down to 25%. And if any motion is detected, it brightens the LED for a short time. And from morning 6 a.m. to evening 6 p.m. during the sunrise and from sunrise to sunset, the lights are always off. So this is a basic block diagram where this is the 8051 microcontroller, which is connected to the LEDs, a PIR sensor, an RTC module, and a power supply. So RTC module gives the present time of the day to the microcontroller, and the microcontroller detects if the LED should be on in either of the three cases. In the third case, that is reduced intensity, if motion is detected by the PIR sensor, then LED brightness turns up for a short duration. So this is the flow diagram. So first we check day or night or time of the day using RTC. If it is daytime, then we turn off all the lights and we repeat the monitoring process. If it is night time, then we have to check the time if it is from 6 p.m. to 12 p.m. or 12 p.m. to 6 a.m. If it is 6 p.m. to 12 p.m., then the brightness is 100% regardless of motion. If it is from 12 a.m. to 6 a.m., then we monitor the PIR sensor. If vehicle is detected, turn lights on at 100% intensity, and if vehicles are not detected, keep it at 25% intensity, and we repeat the monitoring process. So this is the cost analysis. The 8051 IC costed as 95 rupees. The development kit costed as 700 rupees. RTC module costed at 65. PIR sensors costed at 12 rupees. LEDs at 15 rupees and MOSFET at 35 rupees. A total of 922 rupees. This is our circuit. This is the 8051 development kit. This is the PIR sensor. This is the real-time clock module. LEDs to simulate street lights. MOSFET, a resistor, and some connecting wires. So basically how our project works is from morning 6 a.m. to evening 6 p.m. regardless of any motion detected by the PIR sensor, the LED stays off. From evening 6 p.m. to midnight 12 a.m. regardless of any motion detected by the PIR sensor, the LED stays at 100% brightness due to the peak hour traffic and pedestrian movement. From midnight 12 a.m. to morning 6 a.m., when there's no peak hour traffic or pedestrian movement, the LED is dimmed down to 25% to save energy. And when motion is detected, the LED brightens to 100%, and after the motion is gone, it dims down. This is the circuit diagram of our project. This is an 8051 microcontroller which is connected to a crystal oscillator and two 33 picofarad capacitors which acts as the clock. I have not mentioned the power supply because we have used a development kit which has power supply, this clock circuit and everything built into the PCB. Now, the real-time clock module has a VCC and ground, with VCC being connected to plus 5 volt and the ground connected to negative. The SDA and SCL pins are connected to pin 14 and 15, or pin 3.4 and pin 3.5. Now, this is the PIR sensor with VCC connected to plus 5 volt and ground connected to the negative, and data being connected to pin 1 or pin 1.0. The 21st pin or the pin 2.0 is connected to the gate of the MOSFET via a 100 ohm resistor. Now the source of the MOSFET is grounded and the drain is connected to N junctions of the LEDs in parallel. The positive of this cell is connected to the P junctions of the diode in parallel. By controlling the gate of the MOSFET, we can control the brightness of the LEDs via pulse width modulation. This is the code for our project. This is written in embedded C for easy understanding and debugging. We are using the Keel Microvision software for running, editing, compiling, and debugging the code. We first include some header files and then we define pins with PIR being P1.0, gate of the MOSFET being pin 2.0, SDA and SCL being 3.4 and 3.5. Then we define certain global variables such as duty cycle, saved duty cycle, hour, and minute. And these are the function prototypes. So we need all these functions to make the program work. Now, this timer 0 ISR is for PWM generation. This function is required to generate the pulse width modulation. And coming to the main function, we have Tmod, TH0, TL, ET0, EA, and TR0 defined. And if RTC time is not set, then we set the time once and we set the RTC time set as 1. This sets the RTC time once so that the RTC can keep track of the time for the future. And in the main while loop, we read the RTC time. We take the hours and minute of the current time. If hour is greater than or equal to 0 and less than 6, then duty cycle is 25. Else, if hour is greater than or equal to 6 and less than 18, then duty cycle is 0. If R is greater than or equal to 80 and less than 24, then duty cycle is 100. So this is basically 12 a.m. to 6 a.m. This is 6 p.m. to 6 a.m. to 6 p.m. This is 6 p.m. to 12 a.m. And if the hour is less than 6 and more than 18, then we check for the PIR sensor. If motion is detected, the PIR sensor will output 1. And if 1 equals to 1 with a delay, we use this delay to check for any noise in case if there is any noise and to separate noise from actual movement. This is called debounce time. So after the debounce time, we still check if PIR outputs 1. If it is outputting 1, then we save the current duty cycle into a variable called saved duty cycle, and then we change the duty cycle to 100. And with a 3-second delay, we uh we output 100% brightness, and we change the duty cycle back to the previous state. And all of this is done with 200 millisecond delay. Now, coming to the RTC helper functions. So first, RTC gives the value or takes the value in BCD and we are communicating in decimal. So we need to interchange from decimal to BCD and BCD to decimal. These two functions do the same thing. And now for set RTC time, we have taken the current day, date, month, year, hour, minute, and second, and we write it to the RTC via I2C function. So I2C is the communication standard between the 8051 microcontroller and the RTC. Now, the read RTC time function takes in the current time and it converts it into decimal and outputs it. These are the I2C helper functions which start, stop, and write data into the code. And for delay generation, we have used a simple function with two nested for loops.